Okay, so, well, I combined the study session I was going to do last time with this one, so that we probably will not get through all of this, because I have an appointment at 6, and I know you have lab at 6, right? Right, so if we don't get through it, I'll have another one next week, which is the week before finals, yes. So I'll have another one next week to review for the final, if we don't get through all of this. Or I'll have one either way, but I don't think we'll get through all this. So I will go a little bit quick though. So carbonyl compounds, you know most of this. We have a carbon double bonded to oxygen. So oxygen is more electronegative. So when you have a double bond from the carbon and oxygen, the electrons are going to be pulled to the oxygen because it's more electronegative. So this carbon is going to be partially positively charged, which makes this carbon electrophilic, which that's basically the entire point of this whole section, is that carbon being electrophilic. So we have a few different classes of carbonyl compounds. We have aldehydes, where they have one hydrogen, at least one hydrogen, on either side of the carbon. Ketones have carbon groups on either side. And then acyl derivatives have some whatever else thing over here. So like esters, acyl chlorides, carboxylic acids are acyl derivatives. So the first reaction we went over is hydration of aldehydes and ketones. So we can catalyze this with either a base or an acid, but basically the mechanism, you have an aldehyde or a ketone, you hydrate it with water, and you end up with a hydrate, which has two OH groups. So aldehydes will react more favorably because the electrophilicity of the carbon is greater, and that's due to there's not as many. So when you have more alkyl groups around that carbon, it's going to allow the partial positive charge to spread out more, and therefore will decrease that partial positive charge. But when you have the aldehydes, you have one hydrogen, so that positive charge doesn't really have anywhere to go. So aldehydes will react more favorably. So here's the mechanism for that. This is aldehyde or ketone. So the lone pair of electrons from oxygen will grab a hydrogen. This is the acid catalyzed mechanism. And again, we know that that carbon weakly electrophilic, and to react with water, which is a weak nucleophile, that won't work. So we need to do something to this to make it a strong nucleophile, which we protonate with an acid. So lone pair of electrons from oxygen will grab a hydrogen from an acid. That puts a positive charge on this oxygen, and this positive charge will pull the electrons towards that oxygen, which will enhance that partial positive charge on carbon. So that makes this a strong electrophile. So now we have a strong electrophile. Now we can react with water. So a lone pair of electrons from oxygen and water will attack the carbon, which breaks this double bond, and these bonding electrons go to neutralize that positive charge. And you end up with this. So now this double bond is broken. We have a hydrogen added to the oxygen, and we have this OH group here. And from here, we can just deprotonate this, no problem, comes off easy, and you end up with this hydrate, and you reform your catalyst. So we can also catalyze this with a base. So again, this is weakly electrophilic, but in this case, because we have hydroxide, this is a strong nucleophile. So I don't have to do anything to this to make this react with this, because this is weak, but this is strong. So lone pair of electrons from oxygen will attack the carbon, which again breaks that double bond, and you end up with this. And then this oxygen anion will just take a hydrogen from water in the solvent, and then you end up again with the hydrate. And these are all equilibrium reactions. I have a tattoo of this. Did y'all know that?
No,
I do.
That's cool.
Yeah. So these are equilibrium reactions. I don't know that you have to write that. I can't remember, but just keep that in mind.
So, like, will he give us an acid or a base, or will he say show what acid base?
So he would give you an aldehyde or a ketone. I can't remember how he asked this on the test. He will probably tell you either catalyze with base or acid. He would probably tell you to pick one. I'm not sure. exactly. Okay, so example here of the hydration. Okay, so we have this ketone, and this is acid catalyzed from H plus here. So first thing, we'll protonate the carbonyl oxygen. Which makes this a strong electrophile now. So now we can react with water. So lone pair of electrons from oxygen will attack the electrophilic carbon, which breaks that carbon-oxygen double bond, and those bonding electrons go to neutralize that positive charge. So now that whole water molecule is added to the carbon. Now this oxygen has one too many bonds, has a positive charge, but it can come off easy, gets deprotonated, and we end up with a hydrate. Make sense?
These aren't too bad.
Yeah.
Maybe give us something like up top there.
Yeah, I mean, he probably will not focus on these reactions just because they're the easy ones. You may get like, you may or may not be asked the mechanism for this. I can't remember. But you may just have to finish out the reaction or something like that.
Kaylee told me this is the worst final she's ever taken ever.
I don't. I mean, to be fair, I had an open note, an open book.
Really?
Yeah, because I did it 2 years ago in COVID.
Okay.
Yeah. I don't remember it being bad, but
Open note.
it was also open note, open book.
Well,
Okay.
wow, I would.
Yeah. So addition of alcohols is another. It's very similar to the hydration mechanisms. So at this point with this section, some of these steps should be getting kind of intuitive for you. So try to pay attention to what's actually happening and why it's happening, because in these mechanisms there's not like an endless possibility of steps that can be taken. So a lot of these are very similar, and pretty much all of organic mechanisms is based in just what's an electrophile, what's a nucleophile, how many bonds does this have, how many bonds does it want, you know? So just try to pay attention to what's happening, and you can kind of logic your way through it instead of having to, you know, memorize a million mechanisms.
What's the difference between an aldehyde and a ketone?
So let's go back. So an aldehyde has one hydrogen. It can have two, that's formaldehyde, but it has to have one hydrogen connected to the double bonded carbon. Ketones will always have two alkyl groups.
Okay.
Make sense? Okay, but this is the hemiketal reaction thing. So if you start with an aldehyde, mix it with an alcohol, you'll get an intermediate hemiacetal and then an acetal. If you start with a ketone, mix with an alcohol, you get an intermediate hemiketal and then ketal. So this is the mechanism for that. We have aldehyde or ketone. Again, so alcohols are weak nucleophiles. This is a weak electrophile. So if I just mix them together, they're not going to do anything. So I need to protonate this oxygen to make it a strong electrophile. So it has to be acid catalyzed. So that's what I'm doing here. Lone pair of electrons will grab a hydrogen from acid. We'll end up with this. Positive charge on the oxygen pulls the electrons up, which enhances that positive charge on the carbon. So now this is a strong electrophile. And now I can react with the alcohol. So lone pair of electrons from the oxygen and alcohol will attack the carbon, which breaks this double bond, and these bonding electrons go to neutralize that positive charge. So we end up with this. And from here, you can either deprotonate this alcohol group that we just put on and end up with this, which is your hemiketal or hemiacetal. And this does happen to a very, very small extent, but because this OH group likes to be protonated so it can come off so much, this barely happens. So this will happen to some degree, but when it's formed, it goes right back to this. So from here, we have an intramolecular proton transfer from this oxygen here. This hydrogen comes from this oxygen and goes up to here. And that's because, again, the OH group likes to be protonated a lot, so it can come off. So we get this. Again, this oxygen now has 2 hydrogens, has a positive charge. This is a good leaving group. It's water. So it's going to come off. And at the same time, the lone pair of electrons from oxygen, because we took this hydrogen away, lone pair of electrons from oxygen will go to reform a double bond here, which helps push off that leaving group. Okay. So we're losing water here, and then we end up with this. As you can see, this is adjacent to this. So this will react with another mole of alcohol in the same exact way. Okay. So again, this is just another strong electrophile just like this. So we'll react with another mole. Lone pair of electrons from oxygen come and attack that carbon, break the double bond, and the double bond will go to neutralize that positive charge. And now here, so when we got to this step up here, this hydrogen went to this OH group because this OH group likes to be protonated a lot. However, in this case, this hydrogen now has nowhere to go but off, okay? Because if I just put it up here, I'd have the same thing. So there's no driving force for this hydrogen to go anywhere now. So now this hydrogen just comes off. And we reform the catalyst, and we end up with our ketal or acetal product. Does that make sense?
Yeah.
Questions, Haley?
Are we gonna have to show that like middle step where you drew arrows?
I think you can just go straight to here. To the best of my knowledge, I don't think you need to show this because this doesn't really happen because the actual mechanism follows this. So this is your protonated hemiketal, hemiacetal.
Wasn't there a certain, am I thinking there a problem where it stopped there and you didn't? Am I thinking there a problem where it stopped there and you didn't continue on? Like a certain condition where that happened?
So no, there are a very select few hemiacetal hemiketals that are stable enough to be isolated, but to the best of my knowledge, even if they are stable enough to be isolated, they still continue to this to some degree. We didn't learn any that are stable enough to stop there. So all the ones we learned go all the way to here. Questions? All good? Okay. So, an example is, and I'm drawing with my finger, so you'll have to be patient with me because there's no pen here.
Would this work for you? With my Apple Pencil work?
If I can try it, if you don't need it.
I mean, you need it more than I do. See if it.
Let's try it. It does not.
Oh, let's see. Yeah.
Let's draw with my chubby little finger. Okay, there should be a 2 here, FYI. So, acid catalyzed, we're starting with, so this is an aldehyde, right? Because we have hydrogen on one side. So, we're going to protonate that oxygen with the hydrogen to make a strong electrophile. Okay, so the positive charge on oxygen again pulls the electrons towards that oxygen, which enhances a partial positive charge on carbon, which makes this a strong electrophile. So now that I have a strong electrophile, now I can react with the alcohol. So lone pair of electrons from the oxygen will attack the carbon, which breaks the double bond. Bonding electrons go to neutralize that positive charge. So be careful when you're writing this, because sometimes people will like write it like that. Be careful not to do that, because the oxygen is bonding to the carbon. Okay, so make sure your bond is drawn from the carbon to the oxygen. Okay, and this oxygen has a positive charge. It has one too many bonds. So here's our protonated. This would be a hemiacetal, because we started with an aldehyde. So from here, I could deprotonate that, but it doesn't like to do that because that OH group likes to be protonated. So instead, we'll have intermolecular hydrogen transfer, where the hydrogen from the alcohol will transfer to the OH group at the top. Okay, so that puts water at the top. That oxygen has a positive charge. It's a good leaving group. So lone pair of electrons from this oxygen down here will come down to form a double bond, which helps push off that leaving group. So now we have a positive charge on this oxygen here, which this is just adjacent to this. So it's going to react with another mole of alcohol in the same way the other one did. So lone pair of electrons from oxygen will attack carbon, which breaks the double bond. Bonding electrons go to reform the double bond, or neutralize the positive charge, I mean. This is getting slightly messy, so I'm going to write this here and this here. Okay, so that is the one I just added on. And you add the whole alcohol molecule, so it still has a hydrogen on it. Oxygen has a positive charge, but now this hydrogen has nowhere to go but off. So you'll deprotonate. Oh, I'm going to draw this up here. Okay. It's so messy. I'm so sorry. But that carbon has two OCH groups on it, and then the hydrogen and the ethyl group on the other side. Make sense?
Yeah.
I'm sorry. I'm sorry to draw with your finger. Okay, this. So we have CH3, CH2, C. This is bonded to this. This should be up here. This is OCH3, and this should be up here. And this is another OCH3 here. Bonded to hydrogen.
Now, in general, do we have to worry about like R configuration, S configuration, 3D structure? Okay.
No.
That's gone away.
No. Yeah, no, that's not a part of this.
That's a blessing.
Yeah. Okay. All good? Okay, so we have organic reduction, resistance of hydride. So hydride is just an anion of hydrogen, and an anion of hydrogen basically just means it's a hydrogen that's taking a pair of electrons with it. So we have hydride donors, because we can't isolate hydride by itself. And we have lithium aluminum hydride, which is the stronger one, and then sodium borohydride. And this is how they react with electrophiles. So like I said, a hydride just means it's taking a pair of bonding electrons with it. So like when you did carbocation rearrangement, you were moving a hydride, right? Because when you were moving a hydrogen, you were taking that pair of bonding electrons with it. So that was a hydride. So this hydride bond, that's going to be your nucleophile, which will attack an electrophile. And you end up with this. So mechanisms for that. So this is the borohydride. And we don't need to include the sodium or the lithium because they don't do anything. They're just ions. So again, this bond is your nucleophile. Will attack electrophilic carbon, break the double bond. Okay. So with the borohydride, you'll use a protic solvent. So that's either water or an alcohol. When you break that double bond, you end up with an oxygen anion, and then you added hydrogen here. Okay. So now this oxygen anion, this is very unhappy. So it's going to take a hydrogen from the solvent. And that's what a protic solvent means, is it can give away a proton.
What's the Y stand for?
Just whatever. It can either be water or alcohol or whatever alcohol. It's just a variable. So the oxygen anion will take a hydrogen from the solvent, and you'll end up with an alcohol. So for the aluminum hydride, again, we don't need to include the lithium because it doesn't do anything. So this bond is the nucleophile, will attack the carbon, which breaks the double bond. And in this case, because the oxygen has a pretty good affinity for aluminum, which means it likes to bond to aluminum, this whole thing will then attach to this oxygen, which will help to stabilize that oxygen anion. But up here, oxygen doesn't really like boron that much, so oxygen and boron don't talk to each other. But here, this whole thing will attach to the oxygen and stabilize it. And with the aluminum hydride, you can use a non-protic solvent, THF, or a non-protic solvent, THF, or diethyl ether. You cannot use DMSO because DMSO is more or less a carbonyl compound adjacent, so it'll do things you do not want it to do. So those are your only two options. So when we use aluminum hydride, we need to work up or just wash off in some kind of water or dilute acid, which washes off these ions and protonates the oxygen. So again, you just end up with an alcohol. Make sense? Okay, so acyl derivatives can also be reduced, but only with lithium aluminum hydride because it's the stronger hydride donor. Sodium borohydride won't do anything to acyl derivatives, so like carboxylic acids, the esters, they won't do anything to. But we can use the lithium aluminum hydride. And the mechanisms are a little bit different. So for esters, remember esters have an OR group connected to the carbonyl carbon. So again, this bond is the nucleophile, attack the carbon, break the double bond. And again, this whole thing will attach to the oxygen to help stabilize that anion. But in this case, so OR is a good leaving group, which means it can come off easy. So what will happen is these bonding electrons here will come down to form a double bond, which will push off this leaving group, okay? Which will then just give us an aldehyde, right? So if we have this in excess, which we always have this in excess, this will then just reduce further via this mechanism to an alcohol again. So you can completely reduce esters all the way to alcohols too. And also, just don't forget to work up to wash off that aluminum.
Where did the aluminum hydride go, though? So it just breaks off.
I don't know. So it comes off as ions and then just gets washed off whenever you separate the product. Yeah, it doesn't do anything else. I think the borohydride does something and bonds to something else. But I think the aluminum and hydrogen just come off as ions, which just wash away in water. Okay, so for carboxylic acids, which have an OH group connected to the carbon, this one's a little bit tricky, but not too bad. So again, this bond is your nucleophile. So here, when you have an oxygen connected to a hydrogen, so this is a proton. This is a hydride because this hydrogen has this pair of electrons it's taking with it. So when this bond attacks this hydrogen is leaving its electrons with oxygen. Does that make sense? So this is hydride, this is proton. So these two can combine to make H2. And when that OH bond breaks, again, these bonding electrons stay with oxygen. So similar thing, we don't want an oxygen anion, so this aluminum will bond to the oxygen to stabilize that. So you end up with this. Following me thus far?
Yeah.
Okay. And again, this is always an excess, so we'll react with this again. This is nucleophile. We'll attack the electrophilic carbon, which breaks the double bond. Bonding electrons go to oxygen. And again, aluminum will connect to the oxygen here. So at this point, this whole thing is a good leaving group, okay? So this will be adjacent to this, where these bonding electrons will come down to reform a double bond, and this whole thing will come off. And again, we end up with an aldehyde again, which can then go to an alcohol via that mechanism again. Make sense? Make enough sense. Yeah, I don't remember him asking something about this. He may, but I don't remember it. So, okay. We have enough time to go over this. Okay. So this is an ester, right? Because it's an OR group connected here. So So I have my hydride. This will attack the carbon, which breaks the double bond. So I connect a hydrogen to that carbon. This has no change. And this oxygen bonds to the aluminum. So remember, OR group again is a good leaving group. So this oxygen aluminum bonding electrons will come down to reform the double bond, which will push off that OCH3 group. So we end up with an aldehyde. And this lithium aluminum hydride was an excess, so it will react with more aluminum hydride. And then I'll react just like an aldehyde. So the hydride will attack the carbon, break the double bond. The aluminum will bond to the oxygen to help stabilize. And we add another hydrogen to that carbon. So now I can work up because there's nothing else I can reduce. So when I wash off with a dilute acid, that'll get rid of the aluminum and protonate the oxygen. We end up with this, which is just propanol, right? Make sense? All good? Okay. So amines, we know amines are nucleophiles, right? Because nitrogen likes to have 3 bonds, but it has a lone pair of electrons. So those lone pair of electrons can attack electrophilic carbons. So that's what it does here. Attacks the electrophilic carbon, breaks the double bond. So when we add this whole thing here, break this double bond here, we end up with an oxygen anion and then nitrogen cation. So this is negative, this is positive. Neither of these are happy, but if I have an intramolecular hydrogen transfer, one of these hydrogens from the nitrogen will pop on up to the oxygen, which makes them both enough bonds happy. So we end up here. And this nitrogen, again, we have a lone pair of electrons. So this, we've kind of hit a dead end. So we need a protonate so we can keep the reaction going. So when I protonate OH group, we end up with water, good leaving group, right? So the lone pair of electrons from nitrogen will come up to reform a double bond, which pushes off the water, good leaving group. And you end up with a double bond to nitrogen here. And again, nitrogen wants 3 bonds, now it has 4. But this hydrogen is labile, it'll come off easy, and you end up with an imine. So the R group on the nitrogen will shift to either side depending on which one is bigger. Make sense?
What does that mean?
What do you mean?
The R group shifts.
Yes, so this R group on the nitrogen will shift either to this side or this side, depending on which R group down here is bigger.
So will it shift towards the smaller one?
Right, because it wants to avoid steric hindrance. Okay, so if I have a big group here and a big group here, they don't want to be near each other, right? So that would shift over here so it doesn't have to touch the big group.
How crucial is that? Like, will you mark up points if they do that?
I think he said in class so you don't have to worry about it too much, but
Okay.
I wouldn't like lose sleep over it, but I would remember it. Okay. So
There's too many ways to slow sleep. There's too many ways to slow sleep.
yeah, there is much more important things than which side the R group goes on.
What? That keeps me from my 90
Well, I told you so then. Okay, so nitrogen lone pair of electrons attack the carbon electrophilic, breaks the double bond. Which makes an oxygen anion. This is about to get so ugly. Oh no. Okay, let me do something here. Okay, so we added that whole thing to that carbon, broke the double bond. So now I have a positive charge on nitrogen, negative charge on oxygen. So just flip hydrogens around until we're both happy. So one hydrogen from the nitrogen will come up to the oxygen, which gets rid of the positive charge on nitrogen and gets rid of the negative charge on oxygen. So now I'm going to protonate that oxygen to make a good leaving group because I want that to come off. So lone pair of electrons from nitrogen will come up, form a double bond, which pushes off the water. So I lose water. I don't know where to draw this. Okay. So we have NHCH3, 2CH3. So this nitrogen now has 4 bonds. It does not like having 4 bonds, so now it has a positive charge. But that hydrogen is labile, it'll just come off, which reforms the catalyst from up here. I'm going to draw this somewhere else. Okay, so let's go all the way up here.
So that says minus H plus, correct?
Yeah, because the hydrogen from the nitrogen came off. Okay, so we have nitrogen, please, here, okay, CH3. Okay, so we have a CH3 group on the nitrogen, okay?
NCH3.
Yes, so on the right or on the left, we have isopropyl. On the right, we have methyl. Isopropyl is bigger, so the R group does not want to be that close to that group. So our group on nitrogen will be on the right to line up with the methyl because it's smaller. Make sense? Victoria, make sense?
Can you repeat that?
Yes. Okay, so here on this carbon, I have a isopropyl group here, and I have a methyl group on the other side. So the methyl group is smaller than the isopropyl group. So this methyl group on the nitrogen is going to shift to this side, which is going to make it the least sterically hindered.
Okay.
Because if this group was on the other side, it would be hitting this group, and that would cause bond strain, higher energy, not happy. So it'll shift to the side with the smaller group, so it doesn't have to be in contact with the bigger groups and cause bond strain. All good?
Yeah.
Okay, so on to nucleophilic acyl substitution. So again, whole point of this whole section is the carbon is electrophilic, which means it can react with nucleophiles. So if this carbonyl compound has a good leaving group on it, so like the OR groups, etc., the leaving group can be replaced with the nucleophile, which gives a substitution reaction. And the spontaneous reactions of these types are when you go from a less stable acyl derivative to a more stable acyl derivative. You can go backwards, you'll just have to put in energy, heat, etc. So this is the, you'll want to memorize this. Yeah, he's already referenced this like a million times. This is very important. So going this way, the compounds are getting less stable. Okay, so acyl chloride is the least stable of the acyl derivatives. Okay, so this is going to be the most reactive. Okay, so I can pretty much make acyl chloride react with whatever I want because I'll always be getting more stable. Okay, and we have anhydrides, esters, yada yada yada. So the reactivity depends on the leaving group and the electrophilicity. So chloride, for example, this oxygen is electronegative, this chlorine is electronegative, which means this carbon is going to be very electrophilic. And also we know halo groups are good leaving groups, okay? So those mixed together makes this very reactive, makes this want to come off, and makes this want to take in more things. Make sense? And you can apply that to all the rest of them. So, for example, like I said, you can pretty much make acyl chlorides react with anything because they're always going to be getting more stable, and it'll happen spontaneously. So, acyl chloride with water. So with acyl chloride, this is electrophilic enough that I don't have to do anything to this oxygen to make this react with water, because this is electronegative, this is electronegative. So that will make this electrophilic enough to react with this without me having to do anything. So lone pair of electrons from water will attack the carbon, which breaks the double bond. So we end up with oxygen anion, and then a positively charged oxygen here. This bond should be to the oxygen. So this is unhappy, but they're unhappy for opposite reasons. So we'll have an intermolecular hydrogen transfer. This hydrogen will move from this one up here. And again, chlorine is a good leaving group. So lone pair of electrons from an oxygen will come down to reform a double bond, which will push off the chloro group. And I end up with this here. And now this hydrogen labile can come off easy. It'll combine with the chlorine that came off up here to form HCl. And then I'll make a carboxylic acid. Make sense?
Yeah, so then would we repeat that process again to put another LH group on there?
No. So this is not going to be a good leaving group. And this one will not want to protonate easily. I don't know. Maybe you could. We didn't go over that in class, if that's what you're asking. You won't be asked to do that. I don't know if you can or not. Well, no, I don't think you can, because that would mean you have to take this off, and this won't come off.
That's not a good thing.
Yeah, no, that won't come off. I don't think you can do that. So yeah, it'll stop there. And then acyl chloride with alcohol. So basically, you'll have some questions where he'll like give you this and ask you how to make it from something else. So you're going to be looking at the whatever group that's on the acyl compound, and you're going to want to match that to a nucleophile. So we have OH group here, which should tell me, oh, I need a nucleophile with an OH group, which would be water. And here I have OR group. I'm like, oh, I need a nucleophile with an OR group, which would be an alcohol. Does that make sense? Okay. So in this mechanism, it's pretty much the same thing. So lone pair of electrons from oxygen attack the carbon, which breaks the double bond. And we end up with here, again, they're both unhappy, but for opposite reasons. So we'll switch off hydrogens to get here. And then this is a good leaving group. This wants to come off. So lone pair of electrons from oxygen will come down to form a double bond to push that off. And then again, this hydrogen is labile. It can come off, and it will combine with the chlorine here to make HCl, and you end up with an ester. All good? Okay, so esterification is a type of nucleophilic acyl substitution where you go from a carboxylic acid to ester. So in this case, you're going from more stable to less stable. So we have to do something to make it go, which is like in the lab when you did the joint thing and collect the water so it'll go further. So this will not happen spontaneously. It's a reversible reaction. So mechanism, in this case, the electrophilicity of this carbon is not that high. It's not as high as a acyl chloride. So I'll need to protonate to make this a strong electrophile so it can react with the alcohol. So we'll catalyze with acid, and lone pair of electrons will take a hydrogen, protonate the oxygen with which a positive charge, again pulls the electrons up, which enhances the partial positive charge on carbon, which makes this a strong electrophile. So now we can react with alcohol. So lone pair of electrons from alcohol will attack the carbon, break this double bond, and these bonding electrons will go to neutralize the positive charge. And I end up with this here. So again, OH groups very much like to be protonated so they can come off. So hydrogen from the alcohol I just added will transfer to one of these OH groups, it doesn't matter which one, to form water. And then the other OH group, lone pair of electrons from oxygen, will come down to reform a double bond and push off that leaving group. So you'll lose water. I ended up with this, and again, hydrogen is labile, it'll come off, no problem. And you end up with ester. So you see now that like these steps are not endless. There's a lot of the same. So you see now that like these steps are not endless. There's a lot of the same steps for the same reason. You know what I mean? So just try to pay attention to those, and it'll save you a lot of work memorizing if you can try to logic your way through them. Okay, saponification. So this is where we go from an ester to a carboxylate. So, and we act with a hydroxide base. So this is a strong base, strong nucleophile. Lone pair of electrons from oxygen, attack the carbon, break the double bond. OR is a good leaving group. So lone pair of electrons from the oxygen anion will come down, push that off, and we end up here. And now that we have this anion from this that just came off, this is going to want to take a hydrogen from the OH group, which forms an alcohol and a carboxylate. Does that make sense? Because this is more unstable than this is with the negative charge. So this is going to take this hydrogen because this anion is more unstable than this anion. Does that make sense? I'm sensing that was a no from Haley.
So our OR group like comes off
Mm-hmm.
and it goes down there, and where's the hydrogen coming from?
The hydrogen was already there. This hydrogen is this one here. Yeah.
Yes.
Yes.
That group.
Mhm.
OR came off. It's like the hydrogen is after that. And now we just let the oxygen. Yes.
Yes.
It's interesting that we break it off and we break to attack immediately after.
There's chemistry for you. Yeah, and we make soap with this. So like soap, this R group will be like very, 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 very long. And that whole R group will be non-polar. And then this part is polar. So this part is attracted to water. And this whole part is attracted to oil. So we can mix oil and water with soap. Okay, we'll probably stop after this example here. So we have an acyl chloride. Again, this is reactive enough, that carbon is electrophilic enough that I can add water without doing anything to it. So lone pair of electrons from oxygen will attack the carbon, break double bond. So that gives me, So that gives me positively charged oxygen here, negatively charged oxygen here. I'll transfer hydrogen. Make OH group here, OH group here. And this chloro group is a good leaving group. It wants to come off. So lone pair of electrons from oxygen will come down to reform a double bond and push that chlorine off. So now that oxygen is positively charged, but that hydrogen is labile, it comes off.
What does labile mean?
So labile means it is easy to come off. It'll come off without you having to do anything or anything happening to it. It does not want to be there, so it can leave easy. And you end up with carboxylic acid. Makes sense? Okay, so we'll go ahead and stop there, and yeah, I'll go over the rest next week,
Can you send us the
and
whole-
yeah, and I'll review for the whole final next week.
Because